Hello and welcome to first half of our practice exam review. We're going to look at number 1, where we talk about sequences. For this sequence, we're going to take the limit as n approaches infinity, and then we would take the limit. So when we're inside the square root, I can divide all my terms by n. Okay, so I'll divide by n. It's my highest degree. Okay, and I'll see that this term goes to 0. This term goes to 0 as n approaches infinity. This would reduce, give me 4, and this would reduce, give me 1. So I have the square root of 4 over 1, which is the square root of 4, which is 2. So because we get a number, we would say that this series converges because we get the finite number 2. So we say it converges. Let's take a look at part B. We would take the limit as n approaches infinity. This one we could split apart and say we have the 9/10 to the n over 9/10 to the 1 over n, and take the limit of top and bottom. So if we take the limit of the top, we have 9/10 to the n. As n gets really big, this is geometric series where we have a number less than 1, right? So if the number less than 1, the limit is 0. And then for the bottom, we have a limit as n approaches infinity. Now 1 over infinity, this will go to 0, right? So any number to the 0 power is going to equal 1. So we have 0 over 1, which will say that this converges to 0. Okay. All right, let's take a look at number 2. In number 2, we could split this apart. We're looking for the sum of the following series. For part A, we could say that this is 2 to the n over 6 to the n plus 3 to the n over 6 to the n. Okay, so in other words, this is 2/6 to the n, which we could reduce and say this is 1/3 to the n. And then here that this will be 3/6 to the n, so that would reduce and say this will be 1/2 to the n. Okay, so we have n equal 1 to infinity. And so we could find the sum of each of these geometric series. When n equals 1, the first term would be 1/3. Okay, so remember your rule for geometric sum, right? We would have a, which is the first term in the series, over 1 minus r, where r is the common ratio. Okay, so we have 1/3 over 1 minus 1/3. And if you multiply top and bottom by 3, to get rid of the fractions, we end up with 1 over 3 minus 1, which simplifies to 1/2. Okay, for our second part, first term is 1/2 over 1 minus 1/2. Again, similarly, we're going to multiply top and bottom by 2. So that means we have 1 over 2 minus 1, which gives us 1. Okay, we add these together, and we end up with 3/2. Okay, so that would be the answer to part A. Part B, we have 1 over n times n minus 1. This is called a telescoping series. Okay, we could split this apart. We'll do like a partial fractions on this, and we could say we have a over n plus b over n minus 1. Okay, which means we would multiply this fraction by n minus 1. So we have a times n minus 1 plus this fraction on the right we would multiply by n, b times n, and this has to equal our numerator here of 1. Okay, so distribute the a, we have a times n minus a plus b times n equals 1. There's no n terms in our numerator, so we have an plus bn equals 0. And then for our constants, we have negative a equals 1. Okay, so if negative a equals 1, that tells us one thing, that a equals negative 1. So if a equals negative 1, and we look at this statement up here, if a is negative 1, that means b has to be positive 1. Okay, so that means we have a series summation n equals 2 to infinity, and we could write this as 1 over n minus 1 minus 1 over n. Okay, so if we fill in our series, get an idea of what the first few terms looks like, we start at n equals 2. When n equals 2, we have 1 minus a half. When n equals 3, we have 1/2 minus 1/3. When n equals 4, we have 1/3 minus 1/4, so on and so forth. So you'll see that as the series continues, the minus a half and the positive 1/2, these will cancel. The minus 1/3 and the positive 1/3, these will cancel. This will continue all the way down. When n equals n, the 1 over n minus 1 term, whatever that is, will stay, and that will cancel, I should say, and then we'll be left with the 1 over n. Okay, so our summation here would equal, the first term is left, the 1, and then we're left with the 1 over n. And so to see the sum of this series, and if we take the limit of this as n approaches infinity, this will go to 0, so we'll just be left with 1. Okay. Alright, let's take a look at our next problem. For number 3a, we're going to be using the limit comparison test. We're going to be saying that our bn is going to equal, well, I could have n over the square root of n to the 5th, which, if I were to simplify this, this would be n to the 2 over 2 over n to the 5 over 2. And this will simplify to 1 over n to the 3 over 2. Okay, so now this is important because that we know that if we had a summation on 1 over n to the 3/2, this would converge right? This converges by the p-series test because 3/2 is greater than 1. Okay, so this is important to note. So let's do the limit comparison test. This is where we would take our an, which is our original series, divided by bn. Okay, so and we take the limit as n approaches infinity. So we have n over square root of n to the 5th plus 2 divided by 1 over n to the 3/2, which is the same as multiplying by the reciprocal n to the 3/2 over 1. Okay, so multiplying this together on the top, this n is really like n to the 2 over 2 if you want to convert it. So that allows us to combine nicely. So we have n to the 5 over 2 over the square root of n to the 5 plus 2. Okay, still as we take the limit as n approaches infinity. And now we want to divide by n to the 5 over 2. Okay, so if we divide by n to the 5 over 2, n to the 5 over 2, and n to the 5 over 2, okay, as we approach infinity, we end up with 1 over square root of 1 plus 2 over n to the 5th. Now the 2 over n to the 5th, that'll go to 0. So we just end up with 1 over 1, right, which is our limit. And this limit is greater than 0. Okay, and which tells us that if we have a limit and the limit is greater than 0, then bn and an act the same. So because bn converged by the p-series test and also converges by the limit comparison theorem. Okay, let's take a look at part B. Okay, we could rewrite this as limit as n approaches infinity, and this will be n. The e to the negative 1 over n squared, that'll go to the denominator as e to the 1 over n squared. Okay, so if we apply the limit here, limit of the top would just be infinity. Now the limit of the bottom, as n approaches infinity, this exponent is approaching 0. So we really have e to the 0 here, which is 1. So we have infinity over 1, which is infinity. Okay, so we would say that because this is not giving us a finite limit, it's not giving us 0, this would diverge. And the test here would be the nth term test. Nth term test or divergence. And just for reference, you go back to section 10.2. Okay, so this would diverge. Okay, let's take a look at part 4, number 4, part A. Determine whether the following series convergent divergent. Okay, so for this one, we're going to do a direct comparison test. We're going to state that an is 1 over n. Okay, and the series that we're talking about in here, this is our Bn. Okay, so we have, basically we have 1 over ln of n squared is greater than or equal to 1 over n. Okay, we have a big series, okay, and a little series, bigger series, smaller series. Okay, and the rule is, if the big series converges, then the smaller series converges. That's the first scenario. Second scenario is if the smaller series diverges, then the big series diverges. Okay, so here we know that if we had the series over n, we know that this diverges, right, by the p-series test. P is equal to 1. Okay, so our series also diverges. Okay, so we would say that this series also diverges by the direct comparison test. Okay, let's take a look at 4b. 4b, when we look at the series, we could do a limit comparison test here. Okay, our limit comparison for Bn would be 5 to the n over 6 to the n. Okay, so we'll take the limit. The limit as n approaches infinity. We have 2 to the 2n plus 5 to the n over 2 to the n plus 6 to the n divided by 5 to the n over 6 to the n. However, division by this fraction is multiplying by its reciprocal. Okay, so we'll distribute the top, distribute the bottom. So if we distribute the top, we have 2 to the 2n times 6 to the n plus 5 to the n times 6 to the n would be 30 to the n. Distribute the bottom, we would have 10 to the n plus 30 to the n. Okay, now if we divide everything by 30 to the n, and apply the limit as n approaches infinity, we see that we end up with, this is 1, this is 1. This will be, if we look at 6 to the n over 30 to the n, this will approach 0, right? It's like 1/5 if we reduce, and then 0 times anything, so this will be 0. And then this will be 1/3 to the n, so this will be 0. So we end up with a limit of 1, which is greater than 0, which means that an and bn act the same. Okay, an and bn act the same. Okay, if I could fix my spacing here. So remember, Bn was 5 to the n over 6 to the n. Another way to say that is 5/6 to the n, right, which converges. It's a geometric series. Where the common ratio, absolute value of the common ratio is less than 1, and 5/6 is definitely less than 1. So because Bn converges, An also converges by the limit comparison test. Okay, so that's the first half of our review. Go through it, pause it, rewind it. If you have any questions, just ask me during the lecture, or just shoot me an email. Okay? Have a good day, have a good night. See you soon.